John is based in the UK and is the EU Engineering Director for Trimble MEP, a global organization that enjoys a large presence in Brasov. John has more than 20 years of experience studying and working in software engineering, coding desktop and cloud applications, and leading global DevOps and delivery teams.
Yes, I can.
Hey, how are you?
Can you hear me? I'm good, thank you.
Just give us a little bit of a sneak peek about what you're going to talk in the next 45, 50 minutes.
Yeah, no problem. So I'm going to talk about cloud platforms, essentially. The importance kind of today about creating a cloud platform. So anyone that's kind of producing software, and these days it's generally on the cloud. People think about the products that they produce. I'm going to talk more about the platform that often underpins those products and why it's important to focus on that, with some aspects of some of the architectural things that we might want to think about when developing a platform, and then some of the organizational things we want to think about too.
Okay, so if you're ready, we are ready. You can start your presentation.
Great, thank you. Let me just get my screen shared. Hold on 1 second.
Yes.
I'm not sure I can share my screen. It says attendee screen sharing is disabled.
Okay, let's see.
Yep, 1 second. Yeah, you should be able to share it now. You're a co-host.
Yeah, great, thanks. That looks more promising. Okay, and hopefully that's visible
Yeah,
now.
it works, it works.
Excellent, so yes, I can get started then. Well, thanks for the introduction. I'm pretty excited to be here, actually. It'd be obviously better if I could be there over in Romania in person, because it's been almost 2 years, I think, since I've been able to get over there, and I miss coming over. But yeah, as mentioned, I'm John, and I work for Trimble in the MEP division, and that's mechanical, electrical, and plumbing, so it's kind of part of a construction area. So just a kind of vague idea of the sort of area that I work in. And as I mentioned, I'm going to talk about some key concepts that I've seen like in use at Trimble and elsewhere that let you take on some pretty like major challenges with the products and the kind of functions that you provide to your customers and your users. And in particular, as I said, the software platform, cloud-based software platforms, and why it's important to focus on the platform itself. So a bit on the agenda so you can see what's coming. I'm going to talk about what the platform is, at least in my definition of it. I'm going to talk about the architectural concepts I mentioned, and then some of the organizational things as well. Okay, let me move on to the next one. So thinking about the definition of a platform, I think it's like in most presentations, it's always a good place to start, kind of some sort of definition. And if you work in software engineering or study it, which I'm going to guess pretty much everyone here does, you probably hear the word platform multiple times a day, especially at the moment. And it can mean different things in different contexts and kind of different things to different people. And generally, they're all valid definitions of it. So I want to spend a bit of time explaining how I'm using it in this talk. So a good place to start is always Googling the definition for something. So that returns you, I think from Oxford Languages, a raised level surface on which people or things can stand. And we're not talking about people, so let's kind of shorten that a little bit, as a surface on which things can stand. And it's very generic, obviously, but actually it's a pretty good definition to start with. But to go a bit further in terms of technology, I'll talk a little bit about how it's used, how that term's used in the technology area, and some of the things that can be called platforms and are called platforms. Hopefully pull out of all of that exactly what I mean when I talk about it. So the first one to come to is probably YouTube, Twitter, Facebook, those kind of things that are called widely as platforms. And they're mostly platforms in the sense that they provide a technology on which others can distribute content. So in a lot of senses, the product that they provide is the platform. And that's, a platform, as YouTube is, for distributing your own videos or things like that. There's a lot of debate, is Facebook a publisher or a platform? But that's not exactly the sense of the word that I'm talking about. but you can be sure that those companies are definitely developing platforms as I'm talking about them to create their product. And then you've got things like Salesforce, Autodesk have Revit and AutoCAD. We have SketchUp and Tekla within Trimble, and their products, some web, some desktop, and they have a core product functionality within the domain that they operate. But they also allow extension points, usually through some kind of API or plugin architecture. And that allows others to build functionality that runs inside the product. So they're kind of products with platform components. And some of them have been around for many years, so it isn't a new concept. And again, it's not entirely what I'm talking about, but that sort of idea of extensibility is something that a software cloud platform actually really allows you to do. So there's certainly related elements and concepts there. And then, you can't really talk about the cloud without talking about, Google Cloud Platform, Azure, AWS. I think everyone's familiar with those. And they're cloud platforms that provide many different services to allow like hosting your own applications, services, websites, and so on. And they provide base functionality like data storage, messaging, routing, and many more things besides that. And then similarly, you've got things like Kafka, which is an event streaming platform, or Datadog, which is called a monitoring and alerting platform, more specific technology things. And they, again, there's a lot of platform concepts in those offerings, but the type of platform I'm talking about normally uses those as infrastructure components and has something a little bit more domain specific on top of it. So to start describing how I'm looking at the term platform, I'll introduce the star of my definition of it, which is some kind of domain API or a domain service, think of it as well. And it's an API that provides some kind of specific function within the domain that your platform exists. So if that sounds like a confusing description, then as an example, you could think of it as a shopping cart service in a retail domain. It's a particular function in that domain, or a booking service in a hotel domain, could be another one. And I'll talk about, as I get into the architecture side of things, microservices architecture. But essentially, you could think of these as microservices. And these provide all some kind of interface that exposes useful functionality to other consumers, which could be the other services or some kind of UI component. And that interface could be maybe a REST API or something else. Then you've got what I'd call core APIs or services. And these could be ones that you write, or you take something that's already provided as a service from somewhere else. And these don't really handle your domain. They're kind of base requirements of workflows like authentication or authorization, or user licensing, that kind of thing. So they're similar to domain services, perhaps in how they're constructed, but they're kind of a different thing that you might consider, especially as they can often be third-party things that you consume. So it's worth calling those out. And then the services need to work together generally, like each one providing something fairly narrow, some piece of functionality that's useful. But to create really something that your users want to see, it's going to be a workflow that spans multiple ones of them. So maybe they communicate through HTTP or through messaging, something like RabbitMQ maybe. Or you might have an event stream like Kafka that sits in the middle of it all. Something that's providing ways of them talking to each other. And it might actually be a mix of those things too. And then your services need somewhere to live. They need to execute somewhere in the cloud. You want them to scale and be resilient. So it could be that they run as a serverless function, an AWS Lambda or an Azure function, like those ones towards the bottom. Or perhaps they're .NET Core Web APIs and they run inside Docker containers in Kubernetes. Like those infrastructure components, Kubernetes, the Azure and AWS functions, they're kind of key things you need to think about as you think about your platform, like how is it going to be delivered? And that's actually some significant work in building out those kind of pieces as well. And then data. Data is actually a really central piece to the platform. So you're going to have to think about data storage. You could have attached to your services like a Redis cache, Mongo databases, could be items in blob storage. They'll all be part of the picture. And as is logging and monitoring, those kind of base functions need to be considered as part of your platform as well, because they're integral to being able to run a platform in production. So you kind of think of those infrastructure components, the Kubernetes infrastructure, the logging monitoring is kind of the base layer of your platform. And this really kind of builds up the picture of what I see when I'm kind of talking about a platform. And the platform by itself isn't really the goal. Obviously, the goal is to provide useful functions to people, and that depends on your domain almost entirely, doesn't it? So if you think about Amazon, think about Amazon, the retail company, rather than Amazon, the AWS provider, and the kind of goals of that side of the business. I think Amazon's always a good example because it's so familiar to everyone. You've probably used it yourself, so you've got some idea of the sort of workloads of buying things and stuff like that. So their goal, I would say, and it's my interpretation of it, is broadly to allow consumers to find, purchase, maybe rent things, be it a physical item that you buy and is delivered to you, fulfilled, or you're renting a video that you're streaming, or subscribing to a music service, that kind of thing. Lets people buy those, have them delivered. Also lets different sellers, it has a marketplace that they can sell things directly to consumers that get fulfilled by Amazon. That's the goals of Amazon, of the things that it does. So that any platform that they would have supports that goal. And there are different, as you kind of think through all of those different things, there's different applications or products that you might consider on Amazon, kind of different discrete things. Some you'll see as a consumer, some you won't. So you've got like the website itself, and that's got loads of different components to it. You can order things through it. You can check the status of your orders, your deliveries, your recommendations, that kind of thing. And you've got like the Prime Video app on your phone, your Fire TV, your Fire Stick, that kind of thing. And you can buy content through that, or you can access the content that you've already purchased through the Amazon website. And then you've got Alexa devices. You'd think of that as certainly as a discrete product. It has lots of functionality on it, but you can play your music. It can tell you when your delivery of something you've bought off Amazon is going to arrive. And then Amazon have their own internal systems for managing, the warehouses, the stock, the delivery processes itself. Very intelligent systems as well. And they've got all of these different things, and they all link up together. So you order something today on the Amazon website, and then tomorrow morning, your Alexa device is going to ping and tell you that it's going to get delivered. It gets shipped out. You can track the delivery to a degree. It gets delivered to you today. Your Amazon app on your phone tells you that the status is delivered. There's a whole flow of things that have happened there, from you purchasing it to you getting it. And underpinning all of that is a platform of services and components that all work rather seamlessly together and expose data and functionality through these kind of various faces that the apps that you either use visually or through Alexa as well. And the interfaces are all nice, they're all pretty good, they let you do what you need to do, they'll play their part in it. But the power, really, the thing that's tying everything together and that whole workflow and makes it succeed is the platform behind it. And it may be a legend, but supposedly Jeff Bezos famously said nearly 20 years ago, I think it was 2002, everything has to be an API. He had this mandate, they call it the API mandate. There's essentially everything that is developed from now on at Amazon has to have an interface. That's the only way of accessing its data. You can't share data any other way, on pain of being fired. I think it was that strong. Now, I imagine their approach has evolved somewhat, but that kind of shows the thinking that and the place Amazon were at as they were developing this platform, how they saw platforms. So I think once you get a platform in place, or you start to put it in place, it starts to give up new opportunities to link services together, to create new experiences, and pretty quickly as well sometimes. So you can start to build as many applications as you need, as many views on the platform as you need, using those same platform components perhaps, and very crucially the same data and tying them together in new ways that's even ways that you haven't even thought about when you started on your platform. You think about how Alexa's slotted into that whole workflow. That wasn't there at the start 20 years ago. The notion of these components using the same data, which is pretty powerful as well, because you can start to think of new ways of using that data, analyzing it. Data analytics, something that actually event streaming can really help facilitate, is increasingly important to people. And you can expose the platform to others as well. So you can let third parties build off your platform. And potentially there, you're opening up new revenue streams for yourself. That's kind of like I was saying with the products that have a platform aspect to them, extensibility. I mean, that's the value I've seen at Trimble, for example, in the domains that it operates in, and there are many, construction just being one of them. And if you think about that, like, think about what's involved in one of those kind of projects. You've got all these different actors, roles, and companies involved in it. It's like taking a project from its conception all the way through to completion, through design, detailing, estimation, that kind of thing. All these people involved in it. Or in the Amazon example, the process going from a customer placing an order to the delivery driver delivering it. All these other people will be working on it, and components interacting all the way through that, all interacting with the same set of data, workflows between them and across them. And if you focus on that platform that enables it, it really gives you the kind of capability to transform the way industries work, the way that Amazon have, and Trimble do as well. So hopefully that gives a good overview of what I would consider a platform, and what I mean as I'm talking about it now. And why I think it's important to focus the efforts, even above focusing on the individual product offerings that you often think about being like the end goal of the company. You focus instead mainly on the platform that enables those. It is, as I said at the very start, the surface on which all of those features and workflows will stand, regardless of how you deliver them. So paying attention to that service first enables you to create more joined up and innovative features and deliver them faster as well. So I'll start to talk about platform architecture. A couple of key concepts I want to talk about with this, and it's very, very much an introduction, an overview to them, because each of these could really be a whole, and it is a whole series of talks in their own rights. But what I want to do is give a kind of flavor for them, maybe promote some ideas and some thinking, that kind of thing. And the first pattern that I'll talk about is microservices. I've already mentioned it slightly, and I suspect it's fairly well known. So perhaps a deep dive there isn't really what we need at this point. But to talk about microservices, it's useful to start maybe a little bit before microservices. And a traditional development approach, certainly the approach that I experienced when I started my career in application development and continue to use for many years, is what's now often described as a monolith. And in a monolith, you're creating a single solution that could contain many projects, many libraries, modules or DLLs, and whatever's appropriate. It might be structured like this in a kind of n-tiered architecture. You're dividing your business logic, your presentation, data access, and so on. And there are pretty effective ways of structuring and managing such an application. But the primary characteristic of a monolith is typically that it's kind of compiled, distributed, deployed, whatever, as one overall application. There are nuances to that when you think about kind of web applications that are developed as monoliths, but that's broadly a good enough description, I think. But where microservices differ, the contrast really is they break up the functionality of the system along functional domain boundaries to start to create smaller, individually developed, and very critically, individually deployable services, each providing a very specific domain function exposed through an interface, kind of there's that like box wrapping around them. And as they're individually developed and deployed, as they communicate through these interfaces, you have a better degree of flexibility in what they look like. So the internals of each service don't matter to the other services one tiny bit. They can be structured however makes sense for their specific function, as long as you've got the compatibility through the interfaces. So you can make different technology choices between your services as well. So you can choose the technology that fits any of those individual services depending on its needs. And you can have a pretty diverse mix of technologies within the platform. Now, if you've been around a little while, it feels conceptually similar to another approach, which is service-oriented architecture, which you can probably consider as a precursor to microservices. And in that approach, you see the development of individual services in a similar way, discrete pieces of functionality. But by contrast, these are typically stitched together using an enterprise service bus. And that holds a lot of responsibility for orchestrating the interaction between the services and your applications, transforming data as well. And what sets microservices apart, and this is another important concept with microservices, is what Martin Fowler, the kind of design patterns guru, describes as smart endpoints and dumb pipes. So the enterprise service bus you can consider as a smart pipe, because it has a lot of logic built into it and a lot of intelligence in that piece in the middle, outside of the services. Whereas microservices, they're the pieces that contain the intelligence and the logic, and they own their own data. So they're smart endpoints. And then unlike the enterprise service bus, there's no central intelligent controller that's programmed to control the services. Instead, they're communicating to each other through maybe the REST HTTP protocol or a messaging or eventing system, which I'll come to later. But it's the services themselves that largely orchestrate themselves. And you can look at it another way as well, that they choreograph rather than orchestrate. So they each know, their piece and what they need to do. And there's nothing telling each one what it should be doing. Visually, the event picture that's on the right looks similar in layout to the service-oriented architecture, because you've got that kind of thing running through the middle of it. But I think the key point there, key difference, is that in an eventing or messaging system, in this case, it's not making decisions. It's just supplying the messages, supplying the data, supplying the communication. The decisions are still made. The logic is still all embedded into those services. And the picture that I've painted, like in part here, and as I talked about my definition of the platform, is very much obviously microservices architecture. You've got your domain services and your core services. They're all wrapped up functionality into some kind of API that's exposed, some kind of interface. And then they can be used by consumers like your applications and your other services. You can see, I think, hopefully, there are some cons probably to a microservice architecture. And one of those is going to be complexity. You see, like in the picture that I had before, it's, there aren't many services, but when you get to enterprise level platforms, you're kind of scaling out to hundreds of services. To put them all on one page like that, and you can Google large microservice architecture diagrams and you'll find spaghetti. So you really have to think about that as you decide whether or not microservices are appropriate for your organization, I suppose. Because you're creating a distributed system, and distributed systems get complex. Complexity comes in terms of communication. So communication between the services, but also between the teams that are developing them. And there's a very often used law, Conway's law, that kind of states that your organization is, I don't know if doomed is the right word, but maybe fated to create some kind of system that follows the same communication structure as the organization itself. So you need to kind of pay particular attention when you're working with platforms to your own internal communication strategy. But there's also latency, multiple points of failure in that kind of system. Infrastructure management overhead as well can be huge depending on how you're doing it. All things that are factors. But what's a real benefit, I see, and there are a number of benefits, but scalability is probably the thing I'd really call out there. And that's in a couple of senses. You've got runtime scalability, scaling up individual services as opposed to the whole system can be more rapid. generally your services are stateless, meaning that the actual executing service isn't holding any state between requests. You probably have a data store behind it, but you can have multiple services or instances of the same service, I should say, talking to that same data store. So a client can make a request that a load balancer handles and then sends to any one of those instances, and each of them would respond in exactly the same way. So you can easily have multiple instances running. And generally they're pretty small. I mean, that's the micro and microservices. How small depends on you and your use cases, but typically they can be very quick to create and destroy them. That really depends on the technology. Using containers, maybe Windows containers typically take longer to start up than a Linux container. But the startup time in general is fairly small. So you can scale up and down based on demand, which could be looking at the current CPU or memory usage of your instances and scaling up if it's getting high, or looking at the number of messages in a queue that they're working off. You can also, as I mentioned about technology, you've got flexibility there. So maybe you've got a particular service or function that does some more intermittent processing tasks. So you've got spikes of activity where sometimes there's a huge amount that needs to be done, but a lot of the time there's zero usage. So you might make a serverless function for that particular thing, because that lets you scale it and execute it only when it's needed. And cost is an implication there. But other parts of your platform might have more consistent usage, and you have them as like Docker containers in Kubernetes. But as well as that kind of runtime scalability, there's also the scalability of your development itself. If you're thinking about autonomous microservices and you're decoupling them in good ways, then your teams that work on them can work fairly autonomously as well. And it can support much larger development organizations collaborating. And there's definitely things that you need to do to allow that. And some of that I'll talk a little bit about shortly towards the end of the talk. So that's kind of microservices. Obviously, there's some overhead to doing them. So if you're considering platforms, you would think carefully about it. But to me, it kind of, and I think to a lot of people, it seems like the go-to approach, really. But as I said, there are challenges with it, communication being one. So I want to look at one of the ways of approaching that kind of challenge, which is event-driven architecture. And that can actually then help sort of power up your platform as well. So yeah, when we first started creating platforms of microservices, the primary communication kind of default for us was REST between services. And actually, it still is one of the main interfaces that our services provide. It makes a lot of sense, and I think a lot of people do use it as well for that reason, because it is very easy to reason with a request response mechanism. So your customer buys something in their shopping cart and you make a call to the order service and post a new order. Maybe then the order service calls another service to do some kind of stock backend stuff or picking lists for the warehouse, that kind of thing. I mean, these examples are fairly trivial and probably not that real world, but hopefully they'll help illustrate the concepts. You've separated out responsibility along the microservices lines into those different services that own their piece of the puzzle, which is great. You've got your smart endpoints and you're using HTTP protocol and REST as your dumb pipe. But what you can also see in this picture with the lines going from one to the other, that there are dependencies there. There's point-to-point dependencies between services on the platform. And they're coupled. They're not coupled in the way that things are in a monolith, but they're coupled to a degree. And that's something that you might want to avoid. You don't want to create a situation where a change in one area has an impact on other areas. You don't want to get changed, so you actually have to deploy everything at once anyway. So you've probably got a distributed monolith. You've got small services, but they're too coupled. Now, that's by no means inevitable with REST communication between services, but it's just kind of one of those things you really have to think about. And one way of thinking about it is changing how your services communicate in these workflows and moving towards a more event-driven approach, which can open up some other opportunities actually as well about how you extend your platform and how you think about data. So in an event-driven approach, you're elevating the things that happen. They're the events to be first-class citizens in your system. So that any kind of action that would result in a change of state, you emit a structured event notification for it. So you're effectively publishing the fact that this thing has happened, like an order has been raised. And then what I mean by kind of making that a first-class citizen is that you should really start to care just as much about knowing an order has been raised as you do about the data of the order. And that the events that a service publishes and listens for, I think, as well, they become a really integral part of the definition of that service's interface, in the same way that the data structures that gets exposed are. So if you kind of look here, you often think about the interface of a service being its REST interface, its REST API interface. I mean, you can have RPC-based interfaces as well, but this is pretty common. So basically, it's the endpoints that it exposes that can be called to either execute some kind of functionality or retrieve its data. And then you also normally consider the structure of the data when you're thinking about, this is the interface for my service, my order service. This is what an order looks like, and this is how I interact with the service. You need to really expand that definition to also consider the events that are published in it or by it as well. And you might want to document and control the data model of your entire platform. It's a very important thing to do, really, to understand the data that each service exposes and manage some of the complexity and get alignment between your services and how you build your workflows. Certainly on a large platform, that kind of control and knowledge of the data structures is very important. And if you're doing that, creating a data model, you also need to make the events part of that model and consider them just as important. So if we go back to the order example and see how the event-driven approach would change that very slightly, or actually probably more than slightly. Here's the original example again, and that's more command-based. So the shopping cart and the order services are effectively commanding through post requests, and the stock service and the pick list service and the order service itself are kind of responding to those commands. In an event-driven approach, when the user purchases what's in the cart, the shopping cart service there on the left is just shouting about it. It's publishing an event that's saying, it's been submitted, they've purchased it. And then anything that's downstream from that, that in the workflow that needs to respond to it, subscribes to those events and picks it up and does whatever it needs to do, which maybe involves publishing new events that other services listen to as well. So the cart service or the order service, they no longer need to make direct calls to other services. Right? They don't even need to know that the other services exist because they're entirely decoupled. And you can think about how that lends itself well to extendability too, which makes it quicker, really, and cheaper to innovate on it with a pretty simplified example. So suppose that you have this retail system and you want to start offering a customer loyalty program. So whenever a customer places an order, they earn loyalty points. You probably want to update a points balance with every order that gets placed. So maybe you create a new service, let's say a loyalty account service. Now, without events, this is what that change might look like. You'll extend the order service to make a call to the loyalty account service whenever you place an order and you credit an amount of points. But that means you've got to open up the order service code to make the change. You've got to create the loyalty account service. Both services need to be deployed. And you've got a coupling there. You may even have two teams that need to be involved, depending on how you're kind of organized around the services. It's definitely, it's not a huge problem, perhaps. It's always doable, and we do this all the time. But there's an amount of friction that's created there when you're extending the functionality of the system. Contrasting that with an event-driven scenario, where you add the new service and listen out for the existing order raised event, compute the new loyalty balance within the loyalty account service, and there's no other changes necessary there, no additional coupling between the services. And it's an approach with much less friction. Makes it quicker and makes it easier to add on new parts to the system without changing what's already there. So you can achieve that kind of thing using messaging services. There's lots of different varieties of messaging, but there's a publish and subscribe PubSub variant of that. And that's really what you can use here. That's available in things like Amazon Simple Notification Service, RabbitMQ, Azure Service Bus as well. And in this case, the publisher doesn't need to know about the subscribers. There's a thing called a topic. They will publish a message to the topic, and then 0 or more subscribers will listen to the topic, and each of them will get a copy of that message. So that's like, very high level basis of event-driven architectures, and hopefully a quick overview of how it can change your approach from a command-based one to something that's more extendable. And I would expect most platforms to blend these things as well, so REST APIs and messaging as well. And hopefully between that, it makes your platform a little bit more powerful because you can innovate quicker on it and simplifies it in some respects. But another concept with events and with event architectures that takes events and probably elevates them even further is event streaming. And this is the part that I think can really significantly change how you think about data on the platform, and also change how you define the interface of your services. So event streams are actually sometimes referred to as data on the outside. And it's a real kind of paradigm shift from the more traditional approaches. And it's certainly a more complex and advanced topic. And I'm going to scratch the surface of it really, just to introduce it. But if an event is the fact that a change of state happened, or something happened that changed the state, then an event stream is most simply like the log of those events, those facts, just recorded in sequence over time. And at the heart of it, that's what an event stream is. It's a log. And it's normally implemented in a very scalable, distributed way to support kind of large cloud-based systems. Often, real-time data coming in like hundreds, thousands, millions of messages. And it's divided into topics like the PubSub messaging services. And in fact, PubSub is something that most event streams normally support. And the events that are captured in the log, they could live forever. In fact, it's a kind of matter of storage, or you can configure it to perhaps live just for a certain period of time, like depending on your use case. But with that log, you actually have a very full picture of every state change that's happened, perhaps to a particular entity. And you can start thinking about services reacting to the stream of changes as they happen. So if you think about the loyalty account service, that's going to be listening to that order raised event, and it's going to be doing something to it to calculate the loyalty balance. But that too might be publishing its changes to an event stream topic. And in this case, what I've put on here is the loyalty balance topic. And this can be thought about slightly differently then from the order raised, perhaps, because the balance is going to increase with each new order, and it might decrease if you use the points on another order as well. And if you're kind of just capturing the fact that that's happened as a very simple state change that is, this number plus, this number minus, plus minus, that kind of thing as time goes on. If that's all published to the event stream, if you ever need to know the balance, you can just go back over the event stream and add it all up, starting at 0 or the start state, whatever that will be, and kind of replay the events on top of it. And that gives you the current balance of any customer. So now when you're publishing your events from the loyalty account service to a stream, you're actually publishing in that log all of the data that's exposed by that service. So the control of the logic for calculating the account balance and the publishing of the event, that's all still encapsulated within your loyalty account service, as it should be in a microservice world. But now the interface to query that data shifts in a very interesting way. You no longer have to query the loyalty account service to ask for the balance of the customer. It's just available by looking over the event stream. And that's why it's called data on the outside sometimes. that control of the data is retained by the service, but the access to it isn't. It just lives within the streams. If you're using event streaming, you're going to be facilitated by some kind of event streaming platform, such as Kafka. And in addition to the pub sub approach and a very scalable storage mechanism for the event logs, it adds on something called event stream processing, which give you capabilities of actually working with the streams. And in Kafka, you use the Kafka Streams API as one method to access data from your streams. So you can respond to changes in state that happen, as our loyalty account service might do. But then also you have the option of tables as well, that let you kind of aggregate the events that happen into a table that represents a mutable current state, like a traditional SQL table, where each row represents the current state, and that row will change when that state changes, as opposed to immutable events that happen in the log. Once an event has happened, it has happened. Another event may happen later, but that first event still happened. So, maybe something consuming the loyalty account information could access it via a Kafka table that represents the current balance per person. And there's a technology as well, KSQLDB, with Kafka that lets you build stream processing applications in a very lightweight way. And in fact, that loyalty account service could very simply just be a stream processor. And you can think about that as a microservice in its own right, but it's just built using KSQLDB. That's taking the order stream and then emitting another stream, which is the loyalty balance stream, based on what it understands is happening from the order stream. So, you can also combine streams and data in ways that actually start to feel a little bit familiar to traditional relational database systems too. They give you some pretty powerful options of how you consume data. One pattern that people might be familiar with, because again, it's a fairly current pattern, is CQRS, the command query response segregation. And in there, you've got kind of optimizing for two different things. You're optimizing for being able to change the data, like accept commands and state that changes. But then also that model might look different from what you want to do if you want to read it in an efficient way. So you can use event streams and event stream processing pretty well for this. So let's say you want to provide on a screen a summary of someone's account. Let's kind of go back to the sort of Amazon example when you're looking at the website and you want to see an account summary. The commands that change details of the account all happen through various different streams, and it's a very efficient way of us doing it. But when someone requests the summary, to go through and build that up from, these streams may be stored somewhere else, like they may be stored in cached in tables or something, but to go and join that data from maybe orders, maybe you've got that on there, plus you've got the account balance and other bits of information. To do all that when you want to query it is probably a very inefficient query. But you can have a stream processor that aggregates the data as it happens and then spits that out as a more efficient query model to read most efficiently. So when you're querying the account summary service for its data, it already has it in a really nicely digestible form. So, it's just some of the things that event stream processing and event streaming can really give you. There's a lot more that can be said about it as a topic, and certainly a lot to consider. Things like how you design your topics, how you design your schemas, that kind of thing. And I would say one of the definite disadvantages that you see with event streaming is the steep learning curve, that there's so much done that is actually pretty different to how you may have been thinking about data and microservices even before. Look, there is a lot of information out there. And one particularly good resource that I would recommend to anyone is the Confluent website. And just kind of throw up on there. Confluent's a platform that lets you run Kafka. They have a huge amount of information just about event streaming and Kafka that's well worth looking at. So kind of whistle-stop tour of a couple of different architectural concepts. And I think you can see through that developing a platform can be complex. There's lots of different technology approaches in any platform of a real size, lots of moving parts. Developing a platform takes a significant amount of thought and energy, and controlling it can be difficult. It could be a huge amount of chaos. And there are some key practices that I think engineering organizations should consider that might help with that, help kind of tame it a little bit. One of those is feature teams. And a feature team is a team that's responsible for the implementation of a whole customer-focused feature. And that might, and often does, include like front-end and back-end implementation. And in a platform world, it's probably creating domain services, consumer or extending new ones, core services, and that sort of thing to create a whole user-focused feature. And it's a single team that does all of that. So the team's got to be cross-functional. They've got to either have the skills or be able to acquire the skills they need to do everything that that feature requires. Because I mean, if you can help it, I would always say, don't make a distinction between your kind of teams that work on applications and your teams that work on the platform that supports the applications. I think you're much better to think of every team as a feature team that can do application and platform work together. So you don't, I mean, you'll probably have some specialization in areas, domain areas and things like that, but I think it's an approach to work towards, because you want them to be able to work, therefore, without dependencies on other teams. So you don't create a front-end team and a back-end team, because then when you're developing a feature, one team has to wait for the other to do some work and to complete the feature. And then you've got the whole issue of multiple backlogs and bottlenecks to contend with. And with that, obviously, in a microservices architecture, the common pattern is that a team owns a service from the cradle to the grave. And that service provides a discrete bit of functionality, as we just discussed. But end-to-end workflow designed as a feature could span multiple services in the scope of its changes. Hopefully you've limited it as much as possible through decoupling, but that's not always totally possible. But if you follow the feature team pattern, you don't want to be reliant on another team to make some changes. You need a kind of way of handling that. And that's where InnerSource can start to be useful, or at least attempt to be useful. Because again, it's a tricky thing to manage. So what InnerSource is, as it probably sounds a little bit like, it takes the principles of open source, where you've got a project and you're taking input from multiple different parties that aren't directly part of the same team. And you've got a layer of project ownership and oversight that keeps quality high. And you apply that to your company internal projects. So an internal project in the case of a platform dev organization could be a service, domain service or a core service. It could also just be some library components, or it could be some DevOps tooling, that kind of thing. But the idea is to promote reuse and sharing, and then alleviate those bottlenecks that I mentioned that are created when your team depends on something that someone else owns. It also can help you maybe crowdsource some projects, get some more diverse, innovative ideas from across your organization. So you don't wait for another team to make a change. You can make that change. You're empowered to do that, but that's still then reviewed by the owners for some quality assurance and consistency. But to do this, you need a consistent InnerSource strategy that your whole organization understands, and that needs to have a process and a standard for documentation. So a consumer of a project knows how to use it because of the documentation, and they know if they want to contribute it, how they submit changes. There's a process for that that's documented. There might be coding standards embedded into that project documentation. Processes for requesting changes if you're not making them, or logging issues that are found. It needs a strong ownership model as well, where you've got a set of owners, and trusted committer is a role that is commonly used in both open and InnerSource. People who's allowed to review submissions from other teams, and who do you discuss changes with? And that discussion needs a decent communication strategy. Like, how do people reach out to the owners and talk about things on the project? You need a really well-agreed process around pull request submissions and acceptance of them, including things like how much time people can expect to spend within a sprint looking at other people's submissions, because you reduce the bottleneck of having another team make the change, but you want that team to review it pretty quickly. So you need agreements and norms around that. And as your platform grows, or as your kind of organization grows, you need to think about how people will discover these sorts of projects. DevOps is the next kind of key principle I wanted to mention. It's another whole story as well, but it's one of those terms that gets used a lot. I won't go deeply because I'm kind of conscious of time. But you want your teams to be able to build and deploy and monitor everything in production seamlessly. And pipelines to automate everything. It should all be repeatable. Going from code check-in to deployment to production should be a non-event, really. You want it done as frequently as possible. And I'd really recommend spending time up front developing some self-service tools or implementing some existing ones that let teams do it themselves, and educating them on it. And for that, actually, a DevOps team is useful. So in principle, the dev teams own DevOps for their projects, but a dedicated DevOps team that is dedicated to facilitating it is a valuable investment to make. And also making sure your builds and deployment pipelines and things like that are configured at the start before you even get into writing the code is pretty important. Now, my last mention is on shifting left. And you can shift left on pretty much everything. Specifically, I mean on testing and security though here. So shifting left on quality and on testing means moving the testing to the start of the process, designing the tests, building or designing your system in such a way that it's going to be testable. It also means focusing on the lower levels of tests, the things that will run earlier in the process, like unit tests. And there's this classic test pyramid where the majority of your tests are that broad thing at the bottom, and they should be the fast executing and frequently executing unit tests that give you the most early warning if something's wrong. And then as you go up the pyramid, the tests get bigger, they get longer to execute, and they can get more brittle as well as they involve more components working together. So you want fewer of them. You need them, but you want fewer of them. And on security, like, you should care deeply about security because your customers most definitely do. You should think about it from the ground up. Like with quality, you should build security into your systems, into your platform. Things like building vulnerability scanning into your DevOps pipeline, that sort of thing. Security in cloud platform development is a huge concern. So that was a huge amount of topics, I think, really, and it's meant to give you a flavor for what platform development means and what it can do for you. So kind of bringing that all together in summary, focusing on developing a platform as opposed to products can really help your teams innovate quicker. You can use things like microservices and event streaming as enabling architectural patterns, and then also think about different approaches to development processes in organizations, like feature teams, InnerSource, and so on, that will set you up to be successful in platform development. Because it's complex, but it's also incredibly interesting and very powerful. So attention in the right places can really boost your capacity as an organization to deliver. So that that's it from me on the talk. So I guess I can probably open up for any questions if we have time. I'm not sure how much time we have.
Hello. Yeah,
hey.
You're back. So you can turn your camera on?
Yes, I didn't realize it was off. Okay.
Yeah. So any questions for John? Okay.
You're letting me off lightly. Sorry? They're letting me off lightly.
No. I'm gonna ask you a question. So what's 1 second, please. Can you hear me?
Yeah, yeah.
So I'm asking the same question I asked our first speaker from today, Tudor Damian, about cloud or developing on cloud or cloud platforms. They're quite dependent on the logistics and the platform. And we saw that happening with Facebook and WhatsApp just a few weeks earlier. How can we avoid like system shutdowns on large scales?
Yeah, that's a very good question. And you're right. When you're on the cloud, you're at the mercy sometimes of things that are outside of your hand, because you're generally relying on other things provided as a service. Your platforms rely on other people's platforms a lot of the time. And you see that Microsoft and Google and AWS, they're all mature organizations, but they do have problems occasionally. And that can then have a huge impact on your own software that's running in the cloud if something goes wrong. What you need really, you need to think about failovers, making sure you're always in multiple regions. With any of the platforms, you should think about what are your alternative options and how quickly could you move to it. So infrastructure as code from a DevOps point of view is also something you should really invest in. Because how quickly could you spin up, your Kubernetes environment in somewhere else that is currently running? And then monitoring and alerting. So using a platform like New Relic, for example, or Datadog, or something that's giving you a current view of what your system is doing is also really important. So you need to know kind of instantly when you're seeing warning signs of something going wrong, so that you can then react to it, hopefully before it actually becomes a problem. Yeah, I would say, thinking about redundancy, failover, thinking about how you'll respond in a sort of disaster scenario, and then also monitoring to make sure you're aware exactly of what's happening.
Yeah, makes you think of, it looks like a bit of a nightmare when it happens.
Well, yeah, and it's the cloud, so it's going to go wrong at some point. You just need to be able to handle it when it does. It's not you're never going to stop it.
Yeah, Facebook and WhatsApp, it's not, they run on cloud, but imagine if something like AWS or Google or something like that.
Everyone's down.
Yeah, everyone is down. So thank you very much. Really insightful look in cloud platforms and programming and any kind of software related. I guess if anyone who watched this conference can really find you fast on Twitter or something, if they have, it's like
it's find it on LinkedIn probably.
Oh, or LinkedIn, yeah. If it's stuff related to his presentation. Thank you very much, John.
No problem. It's a pleasure.
And have a great day.